Recording, here we go. So, hands up if you've ever heard of sig figs before. Where? Science 10 when you did physics. Liam, did you hear about them before yours in my conversation yesterday?
My friend was talking about them yesterday.
Okay.
He just was starting to do them in Chem.
Nice. Anybody else? Yeah? In Chem. So, sig figs are a wildly useful tool in certain respects. When you guys, like chemistry for example, sig figs are a wildly useful, totally necessary tool for chemists. When you're doing labs in physics, absolutely necessary to work with sig figs. Outside of those kind of two disciplines, sig figs lose some of their oomph, some of their meaning, shall we say. So, here we go. Sig figs. Sig figs are absolutely necessary when making measurements. That's what that's supposed to say up there. It's really kind of small. Absolutely necessary when making measurements. So chemistry, yeah, you need to make the measurements. You need to weigh the stuff properly. You need to measure the volume. You need to calculate moles of things. You want to know at the end of the day what's coming out the other end of whatever reaction you're doing. In a physics lab, things have actual mass. Things have an actual speed. We want to take these measurements and then we're going to calculate things with them, and we want to make sure that we're using as much of the number that is significant as possible and ignoring parts that aren't. And I'll explain to you what I mean here. In physics and in chemistry, the reason why sig figs are so useful is, I'm going to go this way, because they help us estimate error. Now, normally you hear this word error, you think something is wrong, you don't want to be wrong. Should you go off and take chemistry and physics as a discipline, as your post-secondary degree? I have a buddy who went and did chemistry. He's got a PhD in chemistry. He's working at a pharmaceutical company out in Quebec. He made a career of chemistry. If you do that with chemistry or physics, error becomes your best friend. You want error. You want to acknowledge error. You want error to be there, because if error is not there, you don't have a good reason for why you're wrong. But if you can point to errors that show up, now you can blame something else, which is fantastic. Because everything we do in a physics lab, in a chemistry lab, everything we do in these two disciplines, we're relying on other people, whether you realize it or not, to have put things together properly, whatever your measuring tools are. And if you expect them, or whatever machine they're using, to be completely perfect 100% of the time, you're kidding yourself. And so if you can acknowledge the mistakes of the people that came before you, acknowledge the limitations of whatever you're using, now all of a sudden you can say, I'm pretty close, and the only reason I'm off is because of this X, Y, or Z other issue that I can't help. And if you can find out where these errors are, and I'll show you, I'm going to give you some very concrete examples of this. If you can find out where these sources of error are, then all of a sudden that you can say, yeah, my solution is correct, plus or minus whatever my error is. And that's totally acceptable in science. You want error to show up, if at all possible. The biggest mistake, I used to teach first year physics labs at U of E. The biggest mistake that I would see students make all the time is they were too proud to be like, there's error here. They're like, no, I am just that good. I'm like, no, you're not just that good, because I'm not that good. And I've been doing this longer than you guys have. And as soon as a physics student can be like, oh, where's the error? Let's find the error. There's all sorts of errors everywhere. And as soon as you can accept that, recognize that, and embrace it, so much the better. So, I'll give you some examples of what that looks like. Before we do that, accuracy and precision. What's the difference between being accurate and being precise? It's an important part of the conversation around sig figs and error. Oh gosh, put your phone away. Accuracy and precision, what's the difference? As far as you understand them to be, what do these words mean to you? How many of you are like, they're the same thing? How many of you feel like that those two words mean the same thing? Okay? If I asked you if I told you they weren't the same, and then I asked you which one you wanted to be, would you rather be accurate or precise? I don't know, pick an activity. Archery. Let's play archery. Let's go shoot bows and arrows. Would you rather be accurate or precise? Which adjective would you rather define you? You'd rather be precise. Why? Sorry? You like the word more? It sounds better? Okay. What does it mean to you? Okay. So as far as your understanding of these two words, precision is hitting the error in the middle. Okay, then what's accurate? If they're different, they both can't mean that. Diego.
Accurate like being like in a range of being right, but not exactly on the top.
Well, so you're suggesting accurate is like being within the range of being correct, but not exactly correct.
Yeah.
So you're just saying that precise is just better accuracy.
Yeah.
Okay. I can accept that. We're close. Let's give you some definitions. Accuracy. Accuracy, Diego is pretty bang on with accuracy. Accuracy is how close you are to an accepted target. So I've got 3 bullseyes here. Generally speaking, when you're target shooting, you want to hit it in the middle. And so if you had something that looks like this, they're all around the middle, and one in the middle, what could you say about that target shooter? Is that target shooter fairly accurate? Yeah, we want to hit the bullseye. They're all around the bullseye. They got one in the bullseye. They're fairly accurate. We'll call this accurate. Precision is something different. Precision is how consistently you get the same result. So precision and accuracy aren't the same thing. Accuracy is how close you are to the accepted value. Precision is how consistently you get the same result. So this is accurate, but here's an example of something that could be precise. But all my X is up there in that top right-hand corner. This is precise. And Lena said she'd rather be precise, but that was based on the coolness of the sounding of the word. Looking at this definition now, which would you rather be? Would you rather be accurate or would you rather be precise? I guess it depends what you're doing, eh? If you're a Turkish Olympic pistol shooter, if you don't know what I'm referencing, you missed out on a huge part of the summer. If you are a Turkish Olympic pistol shooter, he was both very accurate and very precise. this is what it looks like to be both accurate and precise. This right here if you can only choose one, this one is the better one to be. It is better to be precise, your grouping is really close together, than to be accurate, scattered around what you know the accepted value should be. And the reason for that is this. We don't want if we're target shooting, we don't want all our shots to end up there, but they all did. They all ended up right basically there on top of each other. Has anyone ever shot a gun before? Okay, 2 of you. What kind of gun? Alexis. With a rifle, okay. Was it sighted? Did it have a scope on it? Nice. Vian?
Rifle, pistol, shotgun.
Your rifle have a scope? Okay, let's go with the rifle then. What causes this? Shooters.
Not being sighted in right.
It's not sighted in properly. So, being precise like this, does that have any reflection on you as the shooter? No, this actually means that you're a phenomenal shot. If you have a grouping like this, as someone who uses a rifle, I've also been target shooting. If you can have a grouping like this, this is fantastic. It means you're very good at what you do, and the reason you're not hitting the bullseye is not your fault. It's the fault of the scope. You have an instrument that hasn't been calibrated properly, and once you do calibrate the thing properly, you drag the scope this way a little bit, you drag the scope this way a little bit, and now all of a sudden, all of these shots that were here are now right on target. As soon as you account for problems with the instrument, not problems with you as a person. We call this thing right here systematic error. It is always better to be precise. And if you've never been target shooting, this isn't necessarily, it's not necessarily something to be familiar with, but I'm glad a few of you have been target shooting. My wife is a fantastic shot. Scary, not because she consistently hits the bullseye, but because she does this. She grew up in rural Alberta, and women are just better shots than guys. I don't know. The science says that women, you can be calmer, more stable, and her and I went shooting, that was before we had kids. Her and I went shooting, and she took 3 shots and only found 1 hole. And not because she missed, but because she was just that good. It was wild. And so, but this was what she was shooting. It was up off to the side. We sighted in her scope, and she was bang on every time. My wife is fantastic with a rifle. This, though, is what we're talking about here, systematic error. There's a problem there that's not your fault. Okay, so your desk. I would like every one of you, if you have a ruler, get one out. If you don't have a ruler, I'll provide one to you. You guys are going to take some measurements for me. Using this particular tool. Here you go. And I don't want you to collaborate with anyone sitting around you. I want you to do this all on your own. Oh, you have a ruler. Yeah, that's the one down. If your ruler doesn't have the markings on it you need, I'm happy to lend you one. Because not all of my rulers are created equally. Don't consult, like I said, don't consult anybody else. If you want a tiny one. That'll work. Let's save this tiny one. That guy. There you go. Okay, here's what I want you to do. I would like you guys to measure and record the length and width of your desk using the tool I have provided. Why? Humor me. The length and width, not the thickness. Length and width of the desk. Metric, please. Sorry? I want everything in metric. Yes, centimeters. The length and width of the desk, and I want you to record that value right up here, your desk. Give me those two numbers. Just Curate's on this side too. And back there we've got Bobby and Akash. Yad's over there. Adafa is away. Gurnavan. Simran and Sarah. Okay. Want the length and the width. I'm going to come around and I'm going to get your measurements from you. Okay. 5. Okay, let's keep going. Oh, nice and close up. Okay. 20. What? Sorry. You got this distance. Okay. Oh, 30 point. Okay. 49.7. Okay. Okay. Fine. So working. Again, that's the numbers for me. Yeah. 48. Okay. So 75.6. There you go.
I got rectangular
48.
48 down and 71 width.
71. Okay. Fine. So working. Just curious. Yeah. Sorry. 75 and 60.5 grams. Yeah. 65 and 50. However you choose to. And last but not no, that's not last. Fine. You're good. You're still measuring? You got 75.25. Come back to me. Fine.
and 49.5.
74.5 and
49.5. Was there anybody that was super off?
you put this on the board, you tell me. What does it mean to be super, super off?
Like just.
Well, that's going to be part of the discussion though. What is super, super off?
Yeah. 50.2.
Cool. Okay, so here are your guys' values. You all measured the exact same thing using almost the same tool. And these are the numbers that you guys came up with. So, how close is close enough? You guys, the vast majority, well, yeah, the vast majority of you seem to agree that your desk is in the neighborhood of 75 centimeters wide. And seems to be somewhere in the neighborhood of 50 centimeters deep. That shorter measurement seems to have been the easier one for you guys to take. What did you do? I gave you a tool that was obviously too short. What did we do? Okay, you made markings on the desk. Okay, how many of you didn't bother to make markings on the desk? Okay, makes it a little bit more challenging. How did you do it then if you didn't have markings on the desk? You just held it there and just kind of trusted on faith that it wasn't going to, a breeze wasn't going to come and push your pen or. Yeah, what question? What is the point of the task? So, what if I gave you this tool instead? What if I had given this? This would have been a lot easier, right? This is a tool designed for measuring things larger than a ruler. If we do it with this thing, I'm going to call that thing 0. Ellie, you want to give me a hand here? I want you to hold that guy right there at the 1 meter mark right there on the edge. And then if I hold this thing out here, I'm measuring this thing to be, that was 76 centimeters. Actually, I'm measuring to be 75 point, what's so interesting? Sorry, I'll go over here for a second. Just so your classmates don't have to take my word for it. How is this instrument different than the ruler I gave you? No, look at the divisions. Look at the markings on it. How is it different? Well, the big ones are centimeters, but what are those? Yeah, that's not a proper millimeter. You guys on your rulers between the centimeters should be 10 little ticks. This particular instrument only has 5. Well, yeah, 1, 2, 3, 4, and then to get up to the 6 centimeter is the 5. So this one says, based on this measurement, this one says 75.8. Pretty good. So using a subpart tool, you guys got, lots of you, almost all of you, got very close to what we're going to call the accepted value. Can you hold it there again? What's a problem that shows up with this? Just looking at what's going on here, what's a problem that shows up with this particular tool? The scale's different than the one that you guys used, but I still measured very close to what you guys got. I said 75.8. You said 75.5. Is that point, is that those 3 millimeters that big of a difference? Yeah, right?
When you measure in the middle of the desk, it's not necessarily straight.
Yeah, how do I know this is actually going to be straight?
Put it on the edge.
If I was doing it, well, but then I got rounded corners. So either way, there's going to be problems here. Okay, let's check this side. I got, put that guy there, put that guy there. I got 50.4. let's record my values. I used a different tool than you guys did, and I got 75.8, and what did I just say it was going to be? Let's see, 50.4. So we got some different results here, but how close is close enough? If we're going to call my results the correct ones, I'm not sure we should. I did have the advantage of having a better tool than you guys did. My measuring device at least went the whole distance without you guys having to jump, but given tiny rulers, you guys did pretty good. How close is close enough? Is 76 close enough to 75.8 to say that you did a good job? Akash, are you proud of that number?
Yeah.
You should be. Simran, are you proud of yours? Which is what you should have done. Yeah, no, that's, are you, if I told you to accept, so let's say this was 75.8 and you got 78.8, looking at the discrepancies between the tools we were using, are you proud of that number? Yeah, you should be. Lots of you, given the fact that you guys were at a significant disadvantage, I don't think there's any numbers on here that you shouldn't be, except for one. What's the one kind of outlier here that we might want to question? Does the person with the outlier want to suggest that they're the outlier? I'm gonna go so far as to say even Diego here at 71. Sorry, did you say that should have been 74? Yeah. Even Diego here at 71, like, we're talking 4.5 centimeters different. I think that's pretty good. There's the only number that I kind of question, and I wonder if it was an adding mistake and not a measuring mistake, is this number right here, just Kirit's width. That's the only one where I would look at that and say, I wonder if you added something. Sorry? You added it wrong? Yeah. Did you record some numbers there that you added? Like, what did you? That makes a lot more sense. When something is as clearly different as that tells me that that's probably an adding mistake, not actually a measuring mistake. So when you guys are taking measurements, and a measuring instrument generally has a precision of, or we can say confidently that a measuring instrument generally has a precision of plus or minus half the smallest division. So on your guys' measuring devices, the smallest division is a millimeter. So your guys' we call it instrumental error. On your rulers, you're looking at plus or minus 0.5 millimeters is what yours is. But if we're going to put that all into centimeters, that's going to be plus or minus 0.05 centimeters. That's half a millimeter. Which means that you guys could have theoretically taken all of these values to one more decimal place. On my tape measure, you have to take Cyrus and Lena's word for it, but my tape measure, the smallest division was 2 millimeters. So mine is just going to be plus or minus 1 millimeter, or is plus or minus 0.1 centimeters. So when I'm giving you a measurement, I can't give you any more than a single decimal point, just because of the limitations of the instrument I was using. You guys could have given me up to 2 decimal places based on this, just on the instrument you were using. Generally speaking, we were pretty close though. What I'd like you to do now, just for fun, is based on your length and width measurements that you all have written down, what's the area of your desk? Area for rectangles, length times width. Let's assume those corners aren't rounded. Let's assume they're sharp. Do a calculation with those. What's the area of your desk? You've got it with your hand up. Sorry, I'll start with this. Sorry, what'd you get?
3,830.
Summary?
4,121.
4,121.24. So this is, so we can compare it. Let's keep going down. Granada, what'd you get? Sorry? Hang on a second. Okay. Yeah, do you have a value? 4250 exactly. Nice. Akash? Okay. Bobby?
3,729.26.
Here, Dick? Spirit? 3,784.5. Who's next? Diego?
3,408.
3,408.
Yeah.
Liam was next to Diego.
3,628.8.
3,628.8. Vian.
I did my calculators, I'm still thinking more complication.
Don't you dare. Use long. You just need to start walking into class, giving me your phone, and taking a calculator. You're going to need one every day. Use Alexis's. Alexis, what's your value?
3,727.5.
3727.5. Lena?
3,775.
3775. Granada? 307.71.
307.71.
Akash?
3,762.
3,762. No decimals?
No.
Okay, your day?
3,777.55.
Vian?
3,687.5.
Because you don't have a calculator. Alexis, can you give my I've read all my new accepted value. I don't know. You sure? 3820.32. Okay, so if, just by the fact, the virtue of me being a teacher, being the virtue of the fact that I had the better instrument, by virtue of the fact that I had two people helping me take those measurements, we're going to call mine the accepted values. I had every advantage you didn't have. You were alone with a crappy instrument. I had two people and I had a better instrument. So we'll call mine the accepted value. These values are all really close together. If 75.8 is that I'm accepted with, or the wide part, and the 50.4 the depth, lots of you guys were very close, a couple centimeters different. But as soon as we start to do some math with that, now all of a sudden the discrepancy becomes a lot bigger, yeah? What's the furthest one away from mine? With this one, Diego's value is 400 short, 400 square centimeters short. And Ya is 400 square centimeters extra. So let's compare your measurements with mine. Really, Ya?
Yeah, no, I did it wrong. 3,750.
I was gonna say, yours were bang on. There's no way you should have been so far up. 3750. Okay, so let's get rid of that one. Because his is very close. But even still, look at this difference. I said 75.8, so I had a 0.8 difference in width and a 0.4 difference in depth. And almost 100 square centimeters difference in area. So when we start to actually do things with these values, errors can compound very, very quickly. As soon as we start doing math with these things, we start ramming them into calculators, you do some multiplication, all of a sudden these errors get really, really big. Let's look at Diego's. Diego's values, again, let's talk about Diego's values. Given the limitations, Diego, that I enforced upon you, there is nothing to be ashamed about with these values. 71 and it should have been 76. 48 and it should have been 50. Those are great numbers. You did a great job measuring in a crappy situation. But now I asked you to do something with it, and all of a sudden this is what shows up. What if I asked you to take the volume of something? What What if now we take the depth here, right? Every extra measurement you take, and every extra time you do even a little bit of arithmetic with it, these things start to compound. So this is where error starts to creep in. How close is close enough? Well, if you take my physics lab at U of V, or if you took my physics lab at U of V, within error is the phrase that gets used a lot. But what does that even mean? As far as so when I would teach physics labs at U of V, it's a 3.5 hour block of time, between 3 and 3.5 hour block of time. And the first hour of that time, maybe not quite hour, about 45 minutes, I would spend teaching how to calculate the error for a given formula. So depending on how measurements get combined, the calculations for the errors change. Sometimes they involve some simple calculus, sometimes they involve some really, really ugly calculus, but there are always ways to calculate error based on whatever formula we're using. Let's say it's length times width. For the sake of this course, for the sake of the fact that you guys just haven't done calculus yet, when we do labs, what your guys' close enough needs to be is plus or minus 10%. So this is without. I'm just going to put white out because that's just ridiculous. Oh, my whiteout's gone. Here it is. Without proper error. And in high school, we're never going to look at proper error. We're just going to talk about plus or minus 10%. So let's talk about plus or minus 10%. 10% of 3,820 is 382. So that means any value that is this plus or minus 382 would be considered correct within error. So, Syra, good job. Yup, Simran, good job. Granada, obviously you're good. Yad's good. Akash is good. Bobby's good. Irde is good. Jaskirat's good. Moment of truth. What is 3,820 minus 382? Diego, you're going to be close, man. Oh, 3,820 minus 382. It's going to be 3,400 and something. 3,430. 38. Diego. You are 30 square centimeters short of being correct within error. And you know why that is? And that is all because of these 2 centimeters right here. 2 centimeters. It killed you. Well, didn't kill you. You did great. But 2 centimeters is all it takes to be now outside of accepted error, which means that one's good, that one's good, that one's good, and that one's good. Even though we have huge discrepancy, as big as 4,100 and as low as, well, Diego, 30 square centimeters. Bummer. 13 of the 14 of you managed to get it within error, of what we would consider acceptable error. And this might seem like a huge band. You're like, that is just the way it is. In science, this is what we accept. We say, obviously for some bigger values, 10% is going to be a lot bigger. When we look at some smaller values, you guys are going to calculate for me the acceleration due to gravity. The accepted value is 9.8. 10% of 9.8 is 1, which means you can get as high as almost 11 and as low as just over 8, just under 9, and still be accepted, have an accepted value. So that's instrumental error. We haven't even talked about your guys' error. You bring error too. Instrumentation error has plus or minus the smallest, half the smallest division. So this was your ruler, this was my tape measure, but you yourself are also a source of error. How you choose to take the measurement is part of it. How you choose to measure is part of it. Your biology is part of it. Does anyone know what I mean by when I say biology? Like, what am I referring to there? I'm not talking about, guys, you're just inherently worse at these things than the women are. Like with shooting. Guys are just going to be worse, statistically, than women when it comes to just raw ability on the gun range. It's just the way it is. That's not what I mean here. That's kind of what I mean here. Your biology plays a role into it. I want all you to get your phones up. And I want you to open up your stopwatch. And I want you guys to turn the thing on and off as fast as you can. What's, excuse me, 0.02? Do it again. No, one finger. 2 fingers is cheating. 1 finger. 0.07? That's impressive. What are some numbers we got? We got 0.07. I got 0.11. Sorry? 0.03 with 1 finger. 0.03. What? Show me. Oh, okay. Interesting. I can't get past 0.11. Here today, what'd you get? Sorry? 1 finger. 0.13, so very similar to me. Diego? 0.13, very similar. Sarah? 0.11. Simran? 0.09. Bobby, Akash? 0.09. 0.07. Nice. Okay. So we're close. That's gonna. But even that, as soon as the difference between Granavin, you said it was 0.02. The difference between, we're doing a calculation with time. If your guys' time is, so I guess that's 0.09 seconds different, is going to play a part in what our final calculations are actually going to produce. So when I'm talking about your biology, what we just did is an example of that. Things like reaction time. And that was just a start-stop. Never mind, let's say I dropped something, and you guys had to stop the clock when it hit the ground. The time it takes you to hear the sound, register what that means, and actually push the button is going to be different for all of you. So all of you introduce into this thing a reaction time error, just a time delay in the fact that it actually takes time for the sound to reach you from impact. It takes your brain a sec to realize what's going on, and then to tell your hand, yeah, we need to actually stop the watch. All of that takes time. We don't necessarily recognize a lot of that just kind of in the day-to-day, but all of that's there. And so much of what we do is governed by all sorts of these little errors that we are going to try and pick up. Yeah, Simran. You may. So this is why we introduce a topic like sig figs. Spent the last almost 45 minutes justifying why sig figs are important. This is why sig figs are important. Because we can't say, if I say that I'm correct and that you're wrong, that's not reasonable. But if I say we're all fairly close together, that's true. But to what degree, right? And so we talk about, how close is close enough within error, plus or minus 10%. Lots of what we're going to do as far as what we calculated in class is going to use recorded data. Someone else somewhere took a measurement and you're going to use it. In the lab, it's going to be a different story. You're going to take the measurements and you're going to use it. All recorded data is considered to be significant. However, the last digit in any recorded data, so any data that I hand you, is deemed what we call uncertain. We can't be truly certain of that last digit ever. And so when I get you guys to do labs, we're not going to spend a ton of time in these labs analyzing error like this. But what I am going to ask you to do on every lab that we do is for you to give me an honest idea of what you think or where you think you could have introduced error. Things like reaction time, choices you made to measure are going to introduce error. For those of you who didn't make pencil marks on the desk, one could argue you were at a bit of a disadvantage compared to someone who did choose to make marks on the desk, for example. Okay, error. That's error. Let's talk about the rules for sig figs. Here we go. Significant figures have rules. When we're dealing with things, all non-zero digits are considered to be significant. So, a number like this, 321, has 3 significant figures. They're all significant. That last one's uncertain, but that doesn't mean it's not important. It is significant. Zeros that occur in the middle of the number are considered significant. If there's a digit that comes after them, they are significant. So this thing has 4 sig figs. In a non-decimal number, zeros at the end are not significant. So the only digits we have here that are significant are the 5 and the 2. So this one has 2 sig figs. But if I put a decimal here, sometimes you'll see things like this. There's no digit after that, but there's a decimal point there. This thing, as soon as the decimal point gets added there, that now has 4 sig figs. In a decimal number, zeros to the left are not significant. So if I have zeros here that are to the left of non-zero digits, none of this is considered significant. The only ones that are considered significant are these 2 here. So this thing has 2 sig figs. But in a decimal number, zeros to the right are considered significant. This thing would have 4 sig figs. So if I go back and take a look at this one, if I had 5,200 with a decimal point there, that's 4 sig figs. If I had 5,200.0, one could argue that these 3 numbers are all the same. This one has 2 sig figs, this one has 4 sig figs, this one has 5 sig figs. And here's why. If I told you the answer was a value was 5,200, really, 5,200 is anything between, well, depending on how we're rounding this thing, 5,200 is anywhere between 5,249 and 5,150. This value is anywhere between these two, rounded to 2 sig figs. This one isn't. This one is anywhere between, if I'm keeping the 4 sig figs, this is going to be anywhere between 5,199 and 5,201. Changing the number of sig figs adds a whole lot to what we can say about these values. And then this one's going to start hanging out here in the decimals. The more sig figs we allow, the more precise we're willing to say our answer is. Okay? So that's why these sig figs are as important as they are. So these are the sig fig rules. There's not very many of them. And they seem relatively straightforward. So let's crank these guys out here. Based on those 5 rules, how many sig figs are here? There's 2. Zeros to the right are not significant because there's no decimal there. How many are here? There's 4 there. Zeros between digits are significant. Here, we've got 2, because zeros to the left with a decimal aren't significant. Here we've got 2. Here we've got
1.
because there's no decimal there. Who said 1? Yeah, it's only 1. That's the third rule. In a non-decimal number, zeros at the end are not significant. This is the only digit that we can consider significant because there's no decimal there. This guy, this one has 3 because zeros to the right with a decimal are significant. This guy, 3. And this guy, I heard 2, I heard 4, I heard 6. Because that decimal is there, that makes these 2 significant. And these 2 digits are to the right of other significant digits, which makes these 2 significant as well. This one, all of those digits are significant. That one has 6. Yeah. Okay. So the 1 and 2 are significant. We can agree on that. Because of that decimal, that makes these 2. So it says here, zeros that occur in the middle of a number are significant. And it says in a decimal number, zeros to the right are significant. I'll qualify this piece here. I'll add something to the language here. It says at number 5, in a decimal number, zeros to the right. I'm going to say zeros to the right of sig figs are significant. So if there's a significant figure, a 0 to the right of that significant figure is significant if there's a decimal present. So because this guy here, these 2 are significant, because there's a decimal there, zeros to the right of sig figs with a decimal are significant. That makes these 2 significant. And zeros in the middle of significant figures are significant as well. That makes these 2 significant too. So all 6 of them are. Does that adding of the language there clear it up? Okay. It would have 3 sig figs. Because the first one is significant, the last one is significant, and the 0 in between is. But if you had 0.01, only the last digit would be significant. Because zeros, that first 0 wouldn't be considered significant. Right. Yes. If it's to the right of significant figures, then yes, the zeros are included as well. So addition and subtraction have rules too. Addition, subtraction, multiplication, and division have rules too. When multiplying or dividing numbers, our final answer is always rounded to the least number of sig figs. So I've done the math here already. 250 times 1.15 is 2,807.5. But when we actually do math, we have to round to the least number of sig figs. So how many sig figs are in 250? There's no decimal, so that 0 doesn't count. So this one's just going to be 2 sig figs. How many are here? 3. So that means our final answer should be rounded to 2 sig figs. So how do I round this thing to 2 sig figs? I need to have 2 non-zero digits followed by zeros and no decimal. So what's the number going to be here? This thing would be 290. 290 has sig figs. This value rounds to that value. When you're multiplying or dividing, you round to the least number of sig figs. So this guy here has 4 sig figs. This one has 1 sig fig. When we do the multiplication, we would say, well, this is actually 0.2695. But when because I multiplied, I only want 1 sig fig. What is this value rounded to 1 sig fig? Here, Dave. 0.3. You betcha. And then this guy down here, 200 times 150 is 30,000. How many sig figs are here? So I heard someone say 4, that's correct. How many sig figs are here? How do I write 30,000 with 2 sig figs? It's using a set of tools we've already looked at this year so far. And it's using that last rule. And in decimal numbers, zeros to the right of a significant figure are considered significant if there's a decimal present. So is there any way that I could write 30,000 as 3.0? Because that's 2 sig figs. 30,000 is going to be 3.0. What? Times 10 to the 1, 2, 3, 4. Scientific notation isn't just for cleaning up our math, making the numbers smaller and easier to deal with. Scientific notation is also for having appropriate amounts of sig figs. The only way to write 30,000 with 2 sig figs is to convert it into scientific notation. So that's multiplying and dividing. Adding and subtracting is a lot nicer. And this is the last thing we're going to do today, obviously, because there's only like 2 minutes left. You always round to the least number of decimals. So this one is different. Adding and subtracting, you round to the least number of decimal places. So if I'm going to add these two together, I'll just crank out these 2 examples. You add these 2 together, I'm going to get 82.65. This one has no decimal places. This one has 2 decimal places. So this thing needs to round, because we're adding, needs to round to no decimal places. I would round that thing to 83. And this one down here, 0.6851 minus 0.337 is 0.3481. What would I round that thing to based on the rules for adding and subtracting? This one's got 4, yeah, here it is. 0.348. That one's got 4 decimal places, that one's got 3 decimal places. Final answer rounded to 3 decimal places. So, that is sig figs. Useful for error. I know I haven't given you a ton of time. I would like you to try and get this done. This will be quick, I hope. Give it a shot. I do want you to try those for homework. I know the bell's going to go. Take them up tomorrow. Have a great day. We'll see you later. Sorry I didn't give you any time today to work on them.